Well, how about that lunch? Wasn't that amazing? I do not need dinner now. So, well, welcome. It's 12:45, so we'll go ahead and close these doors in a second and get started. Welcome to the Tennessee STEM Innovation Network Summit. My name is Karen Harper. I work with TSIN this year, putting together a program called Reach Them All. And Reach Them All is a focus on how to integrate computer science and computational thinking into the content you all are already teaching. We want to welcome those that are joining us online. A couple of things. We will be checking the chat box towards the end of this presentation. So if you have any questions online, please put them in the chat box and we will make sure and address them. Also, everything that you see today is going to be available to you all in links and resources. So please know you'll have access to these materials. And we'll explain a little bit more about Reach Them All when we kind of come to the end. So anyway, Karen Harper, I come to TSIN by way of Clarksville, Tennessee. I was there 4 years and just came always as a participant to STEM Summit, so it's really great to be presenting with Katie, and I'll let you introduce yourself.
I'm Katie Stevens, and I am from Putnam County School System in Cookeville, Tennessee. I teach at Prescott South Elementary. I'm the K-4 STEM teacher there.
So Katie and I met in the fall when she joined a team of teachers that wrote some model lessons for the state showing how integration occurs. And so this particular lesson we're highlighting today, and it was not part of the original Reach Them All training, so I see I have some delegates and ambassadors and some computer science folks in here. This is a new lesson for elementary, a 9th lesson you haven't seen yet. So we're really excited to bring it. It's going to be highlighting a 2nd grade standard today on weathering and erosion. So computational thinking, all right? It's a strategic thought process. All K-12 students can do this, can learn through computational thinking, and it can be integrated into all content areas, whatever you're teaching, music, art, science, math. It's an entry point for teachers to learn how to integrate computer science concepts into their curriculum, and you do not need to be a computer science expert or know everything in and out about programming and computing and coding to be able to do this with your students. And as we show you this lesson and you learn more about these integrated lessons, you're going to say, wow, I'm really already doing a lot of that. All right, so we're actually going to start with a short video about what computational thinking is, and Isaac's going to help us toggle between all of these. So let's just take a quick look.
How do you map the entire human DNA sequence? Is it really possible that William Shakespeare wrote all of the works that bear his name? Can you create an intelligent computer program that can write its own novel music compositions? What do these 3 real-life questions have in common? Well, answering these questions requires the use of computational thinking, which is a way of thinking that more and more people are using to solve problems each day. So whether you teach math, science, computing, or the humanities, computational thinking can be a powerful addition to your classroom activities. So what is computational thinking?
Computational thinking is an approach to problem solving. So it's taking apart a problem and figuring out how to attack it using what we know about computation. There's 4 major sort of facets of computational thinking. One is decomposition, breaking something down and figuring out what all the parts are and how you might divide up a task.
And then there's pattern recognition, which is finding similarities and differences between these parts in order to make predictions. Pattern generalization, or abstraction, which is finding the general principles that generate these patterns. And finally, there's algorithm design, which is developing the step-by-step instructions that solve similar problems. People are learning to apply computational thinking to solve problems in many disciplines. When people ask difficult questions, which are more easily solved by computers, or discover insights through analysis of large data sets, they are thinking computationally. Computational thinking is the reason we now have fields like computational biology and computational chemistry. It's also the reason we have new techniques we can use in literature, social studies, and the arts.
So when we start stepping back and looking around us, we see computational thinking everywhere, and it doesn't have to be a scary thing.
Some people confuse computational thinking and computer science, but they're quite distinct. Computer science is an academic discipline involving the study of computation and its application using computers.
Whereas computational thinking is a way we go about attacking problems.
Right, using big picture processes and abstract ways of thinking.
It's something that you could use regardless of whether or not you're a computer scientist or something else. It's a general skill that would benefit you.
Computational thinking increases students' confidence in dealing with ambiguous, complex, or open-ended problems. We believe that all students should learn computational thinking, regardless of subject or age group.
Being able to take a problem, break it down into many different sized pieces, work on each one individually, and eventually bring it all together to solve something, that's a skill that can benefit anyone.
Imagine that you're a journalist and that you want to know what people are saying about an upcoming election. One option is to ask people on the streets about their opinion. Another option is to use a computer program that can analyze social media posts on thousands of web pages in just a few seconds. See, this is an example of the benefit of approaching a problem computationally. So, in the past, if students wanted to see and understand data, they needed to collect the data manually. Now, by developing an algorithm, students benefit from quick results and are able to focus their attention on insights rather than data collection or calculation. By leveraging the strengths of technology, we can focus on our strengths as people, developing insights, analyzing situations, and drawing conclusions. We don't want students to simply use the models that we teach. We want students to be able to create their own models. And to do so, students must find the hidden patterns and insights that can be discovered with computational thinking. Computational thinking is not an additional burden or an extra topic that needs to be taught. Rather, it's an enhancement to your existing curriculum.
So with my students, early on, I just try to use everyday examples to help them understand that it's something that's accessible to them, and then they can start to see how computational thinking does exist in other aspects of their life.
If our students are technology creators, armed with computational skills, they will not only be able to participate and position themselves professionally in a global society, they'll also be able to contribute to society by solving big problems using creativity. So how did we map the human genome? Well, algorithms and computer programs helped us to sequence the millions of base pairs in our DNA. And what about Shakespeare? Turns out computational analyses of the vocabulary, themes, and styles in Shakespeare's works confirmed that he could have indeed written all of the works attributed to him. And that intelligent music-composing computer program? Well, computational thinking was used to find patterns in existing musical compositions and write programs that produced brand new compositions based on those patterns. All of the remaining grand global challenges facing us as humans are problems that require an interdisciplinary approach. By integrating computational thinking skills in all of our subjects, we're preparing students to contribute new solutions to seemingly impossible problems. So yes, many mysteries still remain. For example, what causes gravity? Can we create cures for diseases like cancer? We may not be able to answer these questions today, but perhaps with computational thinking skills, our students will be able to answer these questions in the future.
All right, so just like in the video they shared, at TSIM we focus on 4 of the mini computational thinking strategies: algorithms, step-by-step instructions, pattern recognition, decomposition, breaking things down into smaller, more manageable parts, and abstraction, which is focusing on important information and removing unnecessary details. And especially in science, which Katie's going to share with you a lesson in 2nd grade science, some of the concepts in science can be so abstract. So it's really important when you're showing students how to use an investigation or do a lab or something, that you not just use those physical models, but you bring in computational models to really help them understand. And a computational model is a form of abstraction. And so Katie's going to highlight that today. And so as you can see, that's what we'll focus on as one of our 4 in this next lesson. So abstraction. Abstraction is honestly when working with the delegates and ambassadors and reaching them all across the state, they felt like abstraction was one of the harder ones to kind of get a handle on and really think about, how do I relate that for a second grader? So this is a really great little short 1 minute, 2 minute video on abstraction that you could share with your kids to just kind of show them what it is and how it relates to computer science. And we want to go ahead today and share this with you before we get started in the lessons.
Abstraction is a problem-solving tool that helps you to simplify a situation by removing unimportant information and focusing on what is truly important in a given situation. Suppose you want to find the best bus route between 2 points in a city. There is a lot of information to sort through. However, not all of it is important for this task. For instance, the location of tourist attractions is not important for plotting a route. So when building your abstraction, you might choose to ignore that information. Highways and streets that buses do not travel along are also not helpful, since our goal is to find a bus route. So you might choose to exclude those. Names of neighborhoods are also not important for this task as well. In the end, as the abstraction designer, you might decide that the most important information is simply where to get on the bus, which bus to get on, where to get off the bus, what times to get on and off, and the general shape of the route within the city. These pieces of information, bus number, start, stop times, and route, are essential to the task and are included in the abstraction. Note that even though it features only 5 pieces of information, those 5 pieces can represent many different routes, because every one of them has a start, end, route, bus number, and times. Because abstractions focus on the key pieces of information, they are doubly useful. A single abstraction can represent a whole class of similar things, and they make it easier to understand each one, because there is not extra information present. Every abstraction is built with a purpose in mind. For example, here are 4 different maps, visual abstractions of a city. This map is useful for finding city neighborhoods. This map is useful for finding city streets. This one shows the public transportation of the city, and this one helps them find major attractions in the city. All of these maps show the same city, but each map uses the concept of abstraction to remove what is unimportant and focus on what is important to the user. Abstraction is the process of creating an easier to understand version of a complex system by focusing only on key information.
So when I say weathering and erosion, K-12, there are a lot of things you can do with weathering and erosion. It's a lot. And so in second grade, their focus is, how weathering and erosion change the shape of land. And so we really already, just by that standard, we can bring that down quite a bit. But we are even going to abstract that a little further, and Katie's going to show you through her lesson how we really pulled in and focused on the slope of land, the ground cover, whether it has vegetation or not, and how hard it rains or what that precipitation looks like. So as you can see, we're taking this big concept of weathering and erosion, we're bringing it down to the standard, how wind and water affect the changing shape of land, and then she's really going to focus down on those 3 components with abstraction. So Katie, we're going to let her show you all how this computational model that we're going to use is a great example of the abstraction. She's going to show you the physical model and then bring in how you can do this on a computer. And these are the standards that we're highlighting. And as you can see, we've recently added the computer science standard for second grade. So with that, I'm going to turn it over.
Okay, like Karen said, with Reach Them All, TSIN has partnered with the Tennessee Department of Ed to roll out lessons that are aligned to standards that integrate this computational thinking. So standards that you're already teaching in your classroom, how do you incorporate that? So we're going to take this standard where we're comparing the effectiveness of different solutions from wind and water erosion, and we are going to enhance it through a computational model. And a computational model is an example of an abstraction. So take a minute just to read this little paragraph about weathering and erosion. So again, a standard that you're already teaching, a concept that you're already teaching in your classroom. And now we're going to tie in that computer science aspect with computational thinking. Okay, we're going to look at abstraction and the computational model. So now we're going to go ahead and pass out the lesson plan. We want you to take a few minutes to read through this lesson plan. The standard focuses on, or the standard says wind and water. However, the lesson, we focus more on water erosion. We live in a water-rich state, and our students are more familiar with water erosion. So we're going to focus on that aspect of the standard. So our clear targets, I'll let you read just a moment, and then we'll move on to the clear targets. So the first clear target, I can use computational model to evaluate how the slope of land, rate of rainfall, and type of land cover affect land erosion. So this one is where we pull in the computer science, the computational thinking, okay? The second clear target, I can compare and evaluate different solutions designed to slow or prevent water from changing the shape of the land. And that's exactly what traditionally you would pick as a clear target when teaching this standard. So traditionally, that's what we would focus on. Now we're pulling in that computational model. So now we are going to go into a slide deck for each lesson that was prepared through Reach Them All. You have an online platform through Box with the slide deck. So as you can see, the lesson plan is in there. Also, on the lesson plan online, you'll see that the lesson overview is in there as well. The lesson plan that you have was printed before the overview was moved over into the template. You'll be able to see that anything that needs a hyperlink, a video, a resource, you can click on it straight from the lesson plan. So now we'll go into the slide deck. These slides are prepared for you to use in the classroom as you roll out each lesson. Okay, so we'll start with the clear targets again. You all are familiar with the fact that we're moving into that computational model, that abstraction. So the science connections that we are focused on for this lesson, erosion, flood, and landform. And then abstraction and computational model are those computational thinking concepts that we are going to focus on in this lesson, okay? So just like any lesson that you are teaching in class, you're going to start with that vocabulary. You're going to build the vocabulary, help build that background knowledge for your students. So in this lesson, we've highlighted erosion, which we know is when tiny pieces of the Earth's surface are moved from one place to another, okay? Then we're going to go into flood. We're going to talk about flood, what that looks like, build that vocabulary. Then into landform. So now we're going to tie in those new vocabulary words, abstraction. So we're taking this complex idea and we're moving it down into just focusing on the main idea, okay? And then a computational model is a representation of some part or of a problem or a system using a computer science or computational thinking. And so today we're going to use an online simulator as our computational model to bring this abstraction to life. So for the teacher demonstration, you will need a few just household things and some dirt and some soil. So in the classroom, you would start with this physical model, okay? And then we're going to move into the abstraction. So you're going to need things like 2-liter bottles, string, some cups. You're going to need a pitcher for water, a bucket or a bin tub to collect the runoff, all right? And then you're going to collect soil, grass, and leaves. Okay, so for your physical model, you want to change the variables, right? So in the slide deck, you have a teacher demonstration video, okay? You can choose to show the video in class, and he walks through. He shows you how to do the runoff, how to collect the water, and then he also talks about the different variables. Or you can do the physical demonstration yourself, okay? And so that resource is there for you. So now we're going to look at the online simulator from McGraw-Hill. With this, you'll work with a partner, okay? Then you will want to make sure that you go in first and you are familiar with how the simulator works. And then you will use different aspects of the simulator to change the variables, and the students will change the variables, okay? So with the simulator, you are able to change the slope of the land from 10 degrees to 30 degrees. When you log in, you will have all of the instructions plus a journal area for the students to create their lab results or track their lab results, all right? So they can change the slope. They can also change the variables from vegetation, yes or no, all right? Then the rain intensity, do we want high intensity or low intensity? Then you're going to make it rain. So the simulator will rain, and then they will collect the runoff, okay? And so in their journal online, they can track as the different variables are changed, what the end result is with the runoff, okay? So we've now taken this abstract idea and we've made it, we've taken out and we've weeded everything out and we have the main idea. So we've taken this complex idea and through a computational model, we just have the necessary pieces that we need. So now what we are going to do is we're going to pass out a picture, okay? You're going to evaluate the picture and we're going to talk about how erosion is being prevented in this picture. Per person. Yes, and so.
Actually, it's free. It's linked in there for you in the slides, and it's McGraw-Hill's provided the simulation online free. You know what? I forgot. I'm so sorry. I know the people online can't hear if I don't talk in this. So to access our slides from today's presentation, if you have scanned this and you're on, that slide deck should be uploaded as a resource in this section. And then that simulator is hyperlinked, but you can also type the title of that with McGraw-Hill in and it will come up for you. And they have, McGraw-Hill's provided that on the website as a free access. And just like Katie was saying, it has all the instructions on the left side to show the students how to use the simulator, and then there's a table where they can record their findings as they're flipping through the variables. But yes, that is how you access the website, and then it will get you everything in here is hyperlinked, and that QR code you saw will get you into those lessons. Sorry, I forgot to say that.
And then also at the end of the presentation, we have a QR code that you can scan that will take you directly to the slide deck, the resources, the lesson plan. Yes.
PBL journals, if you're out of school, would this be something that they could do online, but then we could print off and add a hard copy to our PBL student journal?
Yes, absolutely. And it has different journal topics built into the simulator, so you can pick and choose, or also you can just have them write it in as well. But yes, you can print it as well. So you all have different pictures. We have 5 different pictures shared throughout, okay? So you're going to look at the pictures, and you're going to analyze with a partner or somewhere near you, or with yourself, And you're going to talk about or think about how erosion is being prevented in that picture, okay? And then we're going to have a group share out in just a moment. So look at your picture. Discuss with someone nearby how erosion is being prevented.
Putting this slide deck from today into Box in case they don't get it downloaded.
Okay.
It will be there for them.
All right, so let's look at the pictures and let's talk for just a moment. If you had picture number 1, share out how erosion is being prevented in this picture. A barricade, okay. Anyone else with picture 1? Right.
If there's a torrential rain coming, I wonder if they seeded to grow grass there with the hay, and then that's going to keep the dirt from running off.
Right, exactly. So we have that physical barrier, right? Okay, so with number 2, analyze the picture and describe how erosion is being prevented here. If you have picture 2, just the trees, right? The trees and the grass. And from doing the physical model in class, watching the physical model being presented in a video form, you talk about those different variables. And the trees definitely are helping to prevent erosion in this picture, okay? Number 3, the rain garden layout. Right? Yes, okay. So the grass, the plants, the soil, yes. All right. The next one, number 4.
The walls holding it back with the rocks, and then there's also the plants in the crevices to keep things from sliding.
So from sliding, yes. So the wall, the rocks, the plants in there. Anyone else? The mulch. All of those things help us to prevent erosion. Okay, and the last one. The border is helping. The plants, the leveling of it helps as well. Okay? So in this lesson, we have taken that computational model, which allowed us to analyze and collect data. Okay? It was just a simple online simulator, but it turned it into, it took that abstraction and broke it down for us, all right? And through abstraction, we were able to hide all of the irrelevant information and just focus on the problem, and that was the slope of the land, the vegetation or no vegetation, high rain or low rain, okay? And then we were able to make it rain and collect that runoff to track that data. So now we are going to go back in, okay, and we're going to talk about a little bit of how this was using a computational model through abstraction, but how could we take this lesson and how could we make it, how can we decompose it, okay? How could we pattern recognition? So we're going to talk, Karen's going to take over. At the end of your slide deck, you also had the link to the video for the students to see as well.
All right, so if you want to take a moment, and first I would just take a picture of this, and then I would use your phone and you can click on the QR code if you want to pull it up, but it's going to take you into where Katie's lesson plan and the slide deck. And we also just dropped in there, we know that this slide deck is going to be available through TSIN, and this QR code is a resource, but we went ahead and dropped this slide presentation in box as well. So this bit.ly can get you there, and we just put that in the chat for all of you online. And then this QR code takes you, there's also these comparing solutions that you just went through with Katie. That PDF of those pictures are in there as well. All right, so we would like to hear from you. This is a fun audience interaction app called Mentimeter. And so with a Menti, you would take your phone and you'd scan this QR code. It's going to take you to a question. And we would love for you to spend a couple of seconds reflecting on this question. So how does the integration of a computational model, such as that weathering and erosion simulation you saw, enhance the learning of the content standard? All right, so Isaac, when you're ready, we're going to switch over to Menti and we'll see their responses start coming up if it's available. How did the integration of the computational model enhance the teaching of this standard? Take about one more minute to put your thoughts in, and we'll see what you all are saying. So I think there's a lot of power when we use physical models in the science classroom especially to also incorporate that virtual model, that computational model. And I think it's really important that they complement each other. You don't substitute necessarily one for the other. When we have second grade, we are not going to ask them to write the program that creates the computational model, okay? That's what we're going to do with computer science in high school. They're going to write programs that are computational models. So in second grade, how do we get them ready for computational models that are going to be something that they would use later? And that's to start evaluating it. You can ask a second grade student that uses that simulation with runoff, what did you like about that model? What did you wish it would have done that it didn't do, right? So you need to, in the elementary especially, be engaging students with reflection on the model, because that's going to set them up then for middle school and high school in computer science when they take those computational models and they begin writing programs to develop their own. So you guys are all saying it deepens the thinking and provides almost a framework for students to think about the problem, and that problem solving is very big in computational thinking. Allows students to collect data to be analyzed, enriches the learning, allows for student opportunities, makes important parts seen, only in the important parts right. Students can get overwhelmed when we ask them to do a lot. So this kind of hyper-focuses them with abstraction. And then a better focus provides clarity on which variables. I did a lot when I taught in elementary of teaching water and erosion, and I was all over the place. So just to really focus on those three variables and changing them is great. Real world examples. Yes, all of those pictures were taken. We're starting to see a lot of schools do some STEM PBLs with rain gardens. These are becoming quite popular in our outdoor spaces. And so bringing in things they can relate to. Thank you. Thank you very much, Isaac. This was great to take a look. Menti's free. It's a great audience interaction if you're doing PD. You get up to 3 slides, and then if you want to go bigger and more complex, I think they have an upgraded version that you can buy. All right, let's go back to our slide deck then. So I have a question for you, and I want you to, I'm going to divide the room up real quick. So I want you to think about, let's say you had that same standard, comparing possible solutions to water erosion, okay? How would this lesson have been different if instead of a computational model or abstraction, you would have brought in algorithms? So Letitia, your group of 3, how would this lesson have been different if you had to teach that standard using a step-by-step process? All right, in this group of 4, how would this have been different if you were going to focus on patterns as your integration? Okay, not computational models, but patterns. How would you have talked about patterns with this standard? And then I have kind of a group in here, decomposition, breaking a problem into smaller, more manageable parts. How could you teach the standard with that as a focus on integration? So take a few minutes. We'd love to hear from you, because I promise you, depending on which computational thinking practice you pick, that's going to take your lesson an entirely different direction. So have a few minutes to talk about that. All right, 30 seconds, and I can't wait to hear what you're thinking. So when we call on your group to share out, I will probably repeat into the microphone what you're sharing so that our folks online can make sure and hear y'all's responses. So let's start with algorithms. If you wanted to teach weathering and erosion and how, especially water, changes the shape of land, how would you do that by bringing in algorithms?
We were just talking about giving the materials to the students for the actual hands-on experiment.
Sorry. I know you're going to say some really good stuff I'm not going to be able to capture, so we want you to say it right to our friends online.
We were just saying that we could give the materials to the students for the hands-on portion of the activity, and then having them write, okay, what are the step-by-step instructions to complete the experiment?
Awesome. Any investigation has directions, right? So you could have those out. Okay. Hey, what about this group? Pattern recognition. I think one of the gentlemen want to be speaking.
I was just thinking, or we were just thinking, like, when you're looking at comparing the possible solutions, like, what were some things that were common in each one of them? You know, the soil, the vegetation, the slope, things like that.
Perfect.
All right. And our group over here, decomposition.
We talked about how, like, there's one specific lesson that I have done before with flooding and how it breaks down what are the specific components that cause flooding. So like going from highland to lowland, or like clay soil, or like a large concentration of rainstorms. So when you can break it down to these are the small problems that cause flooding or erosion, then what can you do to prevent each one of those small problems?
Did you want to add on?
No, I'm just saying, like she said, it broke it down into parts, and you just focus on that one piece, like.
at a time.
Right, and you were even talking about flooding through glaciers and icebergs and things like that melting, so.
All right, that is amazing. So that's another thing we like to point out. With bringing in computer science and computational thinking, you're not doing anything extra. This is happening, and as you're more comfortable with what computer science is and computational thinking and how that looks, it's just very exciting to see that we really are doing so much of that. If y'all teach science, you know we have science and engineering practices and cross-cutting concepts, and in those you'll remember we have patterns as a cross-cutting concept, and cause and effect is used with conditionals and conditional statements. And then we have analyzing and interpreting data, which is computational thinking. That's a practice in science, and also, yep. And so many of the things we already do and incorporate in three-dimensional science instruction is related to computer science. Reach Them All was a train the trainer model for professional learning that demonstrates exactly what we showed, and we talked a little bit about this being one of the Reach Them All lessons. Each of your school districts has nominated a delegate, and your delegate has a small team of ambassadors, and they have come through training this spring about integration, and they know how to access these lessons, including the one that you saw today, and they will be redelivering all this summer and into the fall, so stay tuned for more information about that. You can read about Reach Them All on our computersciencetn.org website, and there's also a list of your district's delegate in there if you want to reach out to them. But we'd like to thank you, and we'll be here if you have any questions, but we really appreciate you joining us this afternoon. I didn't see any other additional comments on the chat, so I'll stay on if there are any questions, and we can answer them through the website. Thank you.